Hey Psych 213 students, this lecture 8, we're going to be talking about immediate memory. So I'm using the term here, immediate memory, because it's been called many things over the years. It's been called short-term memory, and as we will see, that doesn't do justice to what we use this memory for. It's also called working memory. That's most closely aligned with Baddeley and Hitch's model, but more people are using that more generally. So a generic term for this is immediate memory. So we're talking about here this limited capacity memory store that helps us accomplish a wide variety of tasks. So what we're going to do in this is we're going to talk about this form of memory. So it's labeled working memory here, but this is the memory store that helps us do a wide variety of tasks, including encoding things when we're learning things, but working with information. Sometimes you're working with the information and you don't need to store it for a long period of time, but you need to sort of satisfy some sort of task at hand and work with the information and complete that task. So that's what we're talking about here. And some information might be consolidated into a more permanent storage, but we're going to talk about this box today. And the idea is that maybe there's multiple, or how does this work? And there might even be evidence that there's multiple forms of working memory. So I want to start with some background thinking that led to what's considered sort of the now most dominant model of working memory, and that would be Baddeley and Hitch's model that we'll talk about. And so it begins sort of where Baddeley's thinking sort of began with a couple of other researchers named Atkinson and Schifrin, and they had a model of memory as well. And in this model of memory, they had something they called the short-term store, which functioned like short-term memory, but they wrote some new things about the short-term store. Instead of just talking about something that held information for a brief period of time, they talked about the limited capacity concept that we've talked about before, that working memory has a sort of a limited capacity. But they also said it was a system for holding and manipulating information, so working with information. And so this was the key theoretical piece that Baddeley was interested in. And what he focused on was how this memory system helped us complete a wide variety of tasks, but it also has this limited capacity concept, right? So we use it for all kinds of things in everyday life, but it has limited capacity. So Baddeley's logic was to load up working memory. So he asked people to do 2 tasks at one time, at the same time. This is called working memory load. Now I do want to sort of point out this is not, or gets often confused with task switching. So task switching is when you can do 2 tasks, but you can switch between them. So you do one for a little bit of time, switch and do the other task for a little bit of time, and keep things moving along. That's something different. People study that, but that's something different. Here we're talking about doing 2 tasks at exactly the same time. The idea was you have limited capacity. If you're doing 2 tasks, you should overload working memory and lead to some performance deficits. Excuse me. So that's the idea here. So he started with this first experiment. In the first experiment, he had people do a digit span. So you remember the digit span task where you learn series of digits. They're usually presented to you one item at a time. And he manipulated how many digits. So either there were conditions with either 3 digits or 8 digits, and you should now know that if you're at 8 digits, you're close to the capacity of working memory, right? That's your spans. Remember 7 plus or minus 2 bits or pieces of information. He also, during this task, had people rehearse these digits out loud. Now, I want you to just sort of think for a second why he might actually, why this was necessary. But the idea is, again, gets back to that concept. If you're rehearsing them out loud, you can't switch between the tasks. If you aren't rehearsing out loud, you might rehearse the digits for just a brief period of time, then working on the second task. But if you have to rehearse them out loud, then the researcher knows that you're constantly doing both tasks at the same time. At least that's the logic behind this, right? So the second task he gave people was a reasoning task. So he gave them all kinds of reasoning problems, logic problems. For example, like A follows B, if B then A, and then people would have to answer either true or false. So they're going through this reasoning task and at the same time rehearsing those digits for a digit span task. So the key result here was As he increased working memory load from 3 to 8 items, reasoning time did increase, but the key was working memory was not as overloaded as he thought it would be. That is, rehearsing up to 8 digits. Remember, this is taxing span to nearly its capacity. It increased latency by only 35%, and the error rate was a constant 5%. So one thing is maybe you could do it at the same speed, but you would make more errors. Didn't seem to be the case. So the thing was, he started doing lots of different replications over all kinds of wide range of tasks, got some similar results. Some tasks would interfere, they would overload working memory, while others wouldn't. And so, in Baddeley's mind, this was really hard to reconcile with what would be called a unitary model of working memory, meaning there's only one kind of working memory. So instead, what Baddeley did is he proposed that there was multiple types of working memory, subtypes of working memory. And so he broke it up into, and this is what's considered the Baddeley and Hitch model, broke it up into several different parts. So let me break this down for you. So the first component to his model is something called the central executive. Now this works to control attention to the working memory subsystems. He called them slave systems or subsystems. And the central executive would perform mental operations on information maintained in these subsystems and essentially run or govern all of working memory. So this is a pretty poorly defined kind of concept, but it functions a lot like attention, if you want to think of it that way. This is something when people are studying task switching, they're really looking at central executive processes. That is, how can you switch between different tasks and manage all of that. Remember what we talked about when we talked about practice, and so like think about like the nicer study where the secretaries learn to take dictation and read a novel at the same time. What they're doing is they're really getting more efficient here with their central executive processes, and practice helps the central executive work more efficiently, moving information in and out of these different forms of working memory, these subsystems. But the subsystems that you see here, there's 3 of them listed here. Each one has its own storage system. So each one has limited capacity. So we're going to talk about the characteristics of each here in just a second. But like, for example, the phonological loop has a limited capacity, 7 plus or minus 2 bits of information. So that's what's represented here by this box. And these little tiny boxes would represent bits or information that's in the phonological loop. So for example, if we're talking about like a digit span task, each one of these boxes would be a digit, and you can hold up to 7 plus or minus 2 pieces of information in this phonological loop. You also have the ability to rehearse information or keep it active, work with it. So think like the HM video. So he was able to keep a number active as long as he kept thinking about it. So that's captured here by this little arrow here. So this little arrow here means that you can keep information active in your working memory as long as you're rehearsing it, right? So you could rehearse those digits and maintain them for however long you rehearse them, so that the time lag is not necessarily dependent on any particular factor except for rehearsal. Now, if you don't rehearse it, that information is going to fade very quickly from working memory. Remember the rapid forgetting stuff, right? So we lose information out of our working memory quickly if we're not maintaining it or keeping it active or rehearsing it. So that's what that arrow means. So now these subsystems, each one of them has separate capacity, right? So phonological loop, episodic buffer, and visual spatial sketchpad each have their own storage, each have their own rehearsal mechanisms that you can use, manipulate, work with that information. Each of these subsystems can pass information to the central executive, and the central executive can move information between the subsystems and work with that information in that way. So the phonological loop, let me define that a little bit for you. It's responsible for manipulating and rehearsing verbal information. So this is like your inner speech mechanism. So when you're doing a digit span task, for example, you would be hearing or reading the digits on the screen, and then you're rehearsing them to yourself, talking to yourself. Maybe you're talking out loud, but whatever, that's tapping into this phonological loop form of working memory. So digit span tasks, learning small lists of words, these would all tap into the phonological loop. That's sort of an example of this. So let me skip for the time being. I'm going to skip the episodic buffer because the episodic buffer was added at a later time. So I'm going to come back to this a little bit later in the lecture and define this for you. But let's talk about the visual spatial sketchpad. So the visual spatial sketchpad is responsible for setting up and manipulating, so it's working memory. So setting up, manipulating visual images or spatial information, right? So information where objects are located in three-dimensional space, right? So I could ask you a question that would tap into your visual spatial memory, like how do you go home? What's the directions? Where's your car parked? How many windows are in your house or apartment? So to answer these kinds of questions, you have to think spatially, visual spatial kinds of domains. So this form of working memory, Baddeley and Hitch proposed, was completely separate from this verbal working memory, this phonological loop. Now, one thing that can confuse you is you might be thinking digits are not phonological information. Well, if you're rehearsing individual digits that don't have any particular meaning to one another, then they would be tapping into your inner speech mechanism. So it is the kind of information, but it's also how you're retaining that information that's important here. So let me sort of show you a couple of tasks that Baddeley and Hitch used to tap into the visual spatial working memory. So one is this thing called this pursuit rotor task, where he literally just found sort of tasks that were lying around in his psychology department. And so this is a task where you have this point of light that's moving on this turntable like here, and you take the stylus and you track this point of light. So it's a visual spatial kind of task, the pursuit rotor task. The other thing that they would do that would occupy a visual spatial working memory is they would give you a maze. So your maze would have sort of a start point here, and then they would give you they would present this the first time, and then this would disappear. So this is not constantly visually available. You could do other kinds of tasks, but they give you instructions like move one square to the left, move another square to the left, move one square up, and so on. And what you could do is you track your path throughout this maze, and the person has to sort of reconstruct where they are within this maze, showing that they kept that information in their working memory and updated it when the instructions came down. So these are two examples of visual spatial kinds of tasks. So key evidence for this particular model. So remember, we talked about tasks that interfered with one another and tasks that didn't interfere with one another. That's the key piece of information here. So what Baddeley and Hitch found is that there was a performance cost, meaning performance goes down on one or both of the tasks because this working memory has a limited capacity, but it does so when you have like two phonological tasks. So for example, if you ask people to do that digit span task, so learning a list of digits, and at the same time you ask them to engage in what they called articulatory suppression, so you sort of prevent them from using their inner speech mechanism. So for example, they would just ask them, hey, just say the word the over and over again. So they're saying out loud the, and trying to learn those digits at the same time. You could try it yourself. Go back to that demo that we had for digit span and try it. It's really hard, and it really reduces the number of digits that you can remember because you're not allowed to sort of rehearse those digits on your own because you're saying this syllable over and over again. So what happens is this articulatory suppression occupies some of that 7 ± 2 space in your working memory. The digit spans, they take on or occupy some space on that 7 ± 2 bits of information. And what happens is you lose performance, you lose digits in terms of your memory for that. They compete with one another for this limited capacity, interfere with one another. Likewise, if you do two visual spatial tasks, like if you were to do the pursuit rotor and the visual maze task at the same time, you would see a performance cost. Either the visual maze performance would go down, or the pursuit rotor task would go down, or both would suffer. But the point here is that if you try to do both at the same time, they compete for that limited capacity and you have a performance cost. However, what Baddeley Hitch found is that you don't have any performance cost if you perform one phonological task, like a digit span task, and one visual spatial task, right? So like if you did the digit span and the pursuit rotor, you can do both of these tasks together at the same time equally as well as you could if you did them by themselves, right? So that shows us, or is evidence, that there's no competition there. Must be two different kinds of working memory that's governing performance on both of those tests, and they don't interfere with one another, right? They're separate, independent kinds of systems. So research like this continued for like 25, 30 years of people developing this working memory model or testing this working memory model, and generating basically evidence which is consistent with this sort of view. But let's go back to that episodic buffer. So this was proposed much later, right around 2000, and essentially Baddeley needed a link to long-term memory. So remember, one of the things that's happening here is working memory, there's a link to long-term memory. And so it's thought that this, or postulated that this link between working memory and long-term memory happens through the episodic buffer. Also, at the same time, Baddeley had some patients that had presented some results which were difficult to explain with the current model. So that is, the patients had some impaired auditory span, so this would be a phonological loop deficit, right? However, they could retain 4 digits if presented visually. So presented a different way, they had a little bit better memory. So that was a little confusing, because if their phonological loop was impaired, shouldn't it be impaired no matter how you receive the digits? These patients also had like a 1-word span. So if you gave them a list of individual words to remember, they could only remember basically like 1 word in a list of several. However, they could remember up to 5 sentences. So again, this would suggest a phonological loop deficit, which they clearly had. But remembering up to 5 sentences, that information, if you're listening to the sentences, is coming through the phonological loop. So something's not quite right there. So Baddeley needed a way, or he suggested that the patients had a way of extracting the meaning or the gist. So like the sentences, they could remember the gist or the meaning of the sentences, and that helped their memory. So based on this evidence, he proposed this thing called the episodic buffer, right? So here's the episodic buffer. It is an independent, so limited capacity system that has rehearsal just like the other 2 types. What it does is it binds information from long-term memory, so it could reach in here into long-term memory and bind information from it, or other subsystems. So it could get information from the phonological loop. It could get information from the visual spatial sketchpad. Bind it together in some sort of chunk, and this chunk has a multimodal representation, meaning that it could have visual components, it could have verbal components, but now it's sort of bound together into a new chunk that is something different, multimodal representation, whatever that means. And this system extracts the gist, it extracts the meaning. Now, I want to say that I don't totally understand this. This is a relatively newer thing that's been proposed. People are kind of testing it, trying to figure it out. But this is something that's sort of more so under development, less supported, although, the information changes every day, so there might be much more refinement of the episodic buffer if you went and looked for that information. So I know that might be a little unsatisfying, but I put a paper in Canvas. It's the Baddeley 2000 Trends in Cognitive Sciences paper, where he talks about the model, he talks about the evidence for the episodic buffer, and gives you a little different flavor of it. I also want you to watch this video where Baddeley himself talks about how he and Graham Hitch sort of came up with the model, some of the studies that they did. This will reinforce all of the concepts that we talked about in this part of the lecture, so you can get a better sense of, or you can hear the information again, get a better sense of his model. So I'm going to put a link to Canvas to this video. I encourage you to watch that and take notes on that, just like you, or at least fill in the holes in your notes that you're taking from this video as well. Now I do want to talk a little bit about one other model, just to give you an idea that there are other models out there of working memory, and this is one that I think has a fair amount of support. I think it's really pretty interesting. This comes from Nelson Cowan's model. And so what Cowan says is that working memory is embedded. So it's embedded in long-term memory. So sometimes it's referred to as an embedded model. And so the idea here is, here's your box representing long-term memory. And so each one of these circles would be something that's in your long-term memory, right? So like one of these circles might be, a birthday party from a long time ago, or multiple features from a birthday party. And so the idea here is that we have some information in long-term memory that has been recently accessed, so it's more active, right? So if you recently recalled your mother's maiden name, for example, maybe the circle is a little bit filled in because it's recently been accessed and it's more active. You can access it quicker now. And what, according to Cowan in this model, whatever's highly active is in your central executive, is in working memory. So these stars would be working memory, and the central executive just makes or changes what's active in working memory. So in other words, working memory is in this long-term memory, but it moves around. Sometimes people call this like a spotlight of memory kind of model. I think that's a pretty cool way to think about it. So if you imagine like you're in a dark room and you have a flashlight, whatever is highlighted by the flashlight would be like whatever's in working memory. And you could point it wherever you want to in the room to access that information. But the idea here is that there isn't necessarily a separate working memory store. It's just highly activated long-term memory. So when we learn things, it comes in through the central executive and we'll create new circles or new stars or whatever, and it'll be highly active. And if we don't use it, it'll disappear. It'll be lost from working memory, for example. But the idea is that it's sort of working memory is information in long-term memory that's in a highly active state. It's going to decay really rapidly unless it's refreshed or rehearsed. This is all the same stuff that we've been talking about before, like remember rapid forgetting or HM remembering a number. And of course, if you take additional time, effort, and encoding, the information in working memory can become consolidated or put into long-term memory for more permanent storage, right? The central executive also has limited capacity. Remember that 7 plus or minus 2 stuff. However, the number of representations in long-term memory is really many more, so it could activate whatever it wants to activate, right? So all of the other lessons, all of the other information that we have still fits within Cowan's model and can be sort of explained by Cowan's model. Let me give you one piece of information, one example of how there is support, but there is more. I have a article in Canvas. This is the 2010 Richter et al. Paper. You can read more about Cowan's model. Again, you'll get a bit of a summary of Baddeley and Hitch's model, and then just summary of how Cowan's model differs to sort of fill in the details for you. This is much more just an quick overview. But let me give you a little bit of evidence that sort of supports this. So one study looked at people who were retaining verbal meaning in working memory. Right, so they had semantic information. This is verbal meaning of words, right? And compared that to activation of phonetics, how words sound, right? So now in Baddeley and Hitch's model, these are both verbal information, so they should tap the same form of working memory, right? The phonological loop. So Baddeley and Hitch is predicting that both of these tasks, whether you're maintaining meaning in your working memory or whether you're paying attention to the phonology, should both tap into the phonological loop. However, Cowan's model says, hey, whatever the organization of long-term memory is, this is what it will be like in working memory. And there had been some prior studies, right, which had shown that retrieval of semantic information activated the left frontal areas in the brain and from long-term memory. So if we just like ask you about meanings of the words, this area is going to be active. This left frontal area is going to be active. If we ask you to pay attention to or attend to sound, you're going to have this area of your temporal cortex, right, which is associated with processing hearing. That's going to be the auditory cortex is going to be active for people processing phonological information. So that's whatever exists in long-term memory. So in these two tasks, they looked at what areas were active in the brain. And as it turns out, semantic information in working memory activated the left frontal area. And when people activated phonological information, you had this auditory cortex area that was active. So the point here is that Baddeley and Hitch would predict it's the same form of working memory, so it should be the same brain area that would be active. Here we have different brain areas that are active, which are consistent with whatever the organization of long-term memory. So that would suggest that Cowan's model does a better job predicting these kinds of results. Now, I want to point out that we could go on and on about this. I could share lots of other data where Baddeley and Hitch's model makes a better prediction than Cowan's model. And we could even find data where both of their models don't make good predictions. The point is, they're trying to sort all this stuff out. And these models, or developing these models, exist when you're sort of continually creating experiments, looking at the evidence, and refining the models based on new evidence. So this is sort of what's happening. But I do want to wrap up this lecture with some just overview of some things, some important messages to sort of take away from this particular lecture. So we've been talking about immediate memory. So working memory or immediate memory, it has limited capacity, right? And so our performance is going to suffer when we overload that capacity. So for example, if I'm speaking too quickly in this video, the nice thing that you can do is you can pause this video. But if you were in class and I was talking too fast, you might lose information that I would say. You can't take notes that fast, and I would overload your working memory capacity and you would lose information. You wouldn't have access to that information at a later time, right? So we all are aware that our limited capacity gets overloaded. This is when you sort of feel overwhelmed, if you will, with a particular task, right? So work on ways to reduce the capacity, slow things down if you can. Practice is a really important thing that will, as we learned, can free up attentional resources and help with your working memory capacity issues. The other key piece of information is that some tasks interfere with one another and others don't. Right, so that's certainly been borne out in all of this literature over time is that some tasks, like two phonological tasks, they're going to interfere with one another. But one phonological, one visual spatial, much better, much less interference, much more likely to be able to manage those tasks at the same time. Now, real world tasks involve a mix of memory demands. So if you think about even like something like driving, that's going to be primarily visual spatial, where you're thinking about, keeping your car on the road, paying attention to traffic around you. But it could involve a mix of verbal tasks, particularly if somebody's given you directions to go somewhere. Well, then you have to listen to the directions. That's going to involve phonological loop. Then you're going to have to convert those verbal instructions into some sort of visual spatial code. And you can quickly see, or maybe understand, why that when you get lost, all of a sudden that task becomes much more difficult because you're having much more interference as you're trying to convert verbal instructions into a visual spatial form of code. You have this interference that's going to take place, right? So real world tasks often involve a mix of memory demands. It's rare, these cases that I was talking about, these experimental laboratory conditions, much more pure tasks, pure phonological, pure visual spatial, but our real world tasks, it mixes these up. So because of this, multitasking is very difficult to achieve because oftentimes it's going to involve multiple memory systems and it's very easy to overload your working memory capacity. So this concept of people saying, oh, I can do multiple tasks at one time, rarely is that the case. That's borne out in a lot of the cognitive psychology literature. You can do better with a lot of practice, but it's still, the reality is you most likely can do your best performance if you're focused on one particular task rather than doing multitasking. Now, I do have some evidence to sort of share with you that speaks to this. So in 2018, we published a research paper where what we did is we had people use, these were student subjects, and we recorded their brain activity while they were doing a task. In this case, it was an executive function task, so just paying attention to some numbers in a visual array. And they did so without any distraction. And then we had them do the task again when they were using their smartphone at the same time. So we gave them some tasks. They had to look up articles on their smartphone, so they were navigating through the web using their smartphone. And what we did is we not only measured performance and performance suffered, but we looked at brain activity. And the brain activity is represented here by these event-related potentials, these ERPs, shows you the point here is that the distraction is much lower. We did this again with a gambling task, and we got the same sort of reduced activity when you were distracted versus when you're not distracted, right? So this is consistent with other research studies that basically are showing that not only is there a performance problem, but your brain just can't handle doing two things at the same time. It's not at the same level, right? So the idea here is that multitasking is very difficult to do. There's a cost to it. We have limited capacity, right? We have limited attention. We have limited working memory capacity. It's very easy to overload that. You can do better, and you can switch with practice, and you can switch between the tasks, but it still has some costs. So that's the end of our immediate memory, and I'll see you with the next lecture.